back when we started alpha carbon things, because why all the alpha carbon things aren't all, together, I will never know. Oxidation reduction, you can tack that on at the very end. There's no good reason to put that in between. I don't know. So racinization is basically if you have a stereocenter alpha to a carbonyl, well, you can do tautomerization, right? Keto-enol tautomerization. And when you do that, this whole thing is planar. This whole thing is planar, right? You've got these two carbons, and they're both planar. So this carbon that used to be a stereocenter is now just trigonal planar, and could be attacked from the top or from the bottom, and you could get either enantiomer back out at the end, right? And it's not stereo selective because, well, it's flat. What's the difference between them? There's not. So basically, if you have a stereocenter alpha to a carbonyl to any carbonyl, you don't for very long, or you're not going to for very long, if there's any acid or base around. And I mean, honestly, I bet it'll happen eventually in any protic solvent. Like if you have something like this and you have some water around or something, eventually, if you leave that in the fridge long enough, even then it will probably end up with a racemic mixture of these eventually. But the more acid or base you have, the faster this goes to get there. So, yeah. And it's the same mechanism as the tautomerization that we learned. So, yay. Deuterium exchange is another reaction we can have at the alpha carbon. So, any hydrogens that we have on the carbon alpha to a carbonyl are going to be exchangeable, right? And I think I've used this term in class before, labile. Have I said that before? Okay, I don't know. I use that term a lot, and I definitely didn't define it. So mostly metal people use that term. Labile just means it can, whether or not this is actually a thing that will detach and go do something useful, it's really just, it'll detach and reattach all over the place. They'll just keep doing that. So acidic hydrogens are pretty labile. If you have, you can assume that if you take an acid and you put it in anything protic, so there are protons that can be stolen from other things and they can all exchange, that if you label, let's see, we haven't done this yet, but we're going to, and that's acidic, right? This guy can come off, this is acidic. So if you put this in, I don't know, in some water, and this guy is actually labeled, but there's a bunch of water and maybe even a little bit of acid or base. Base specifically, but honestly, you don't even have to have that because this is just, they can trade, right? So this labeled hydrogen isn't going to be labeled for very long. Some of them will be labeled and some of the labeled ones will be on the water and it'll just be all over the place. So, what we can do is we can take one of these and we can label the alpha hydrogens by just, instead of water being around, there's only D2O. So there's only a little bit of, only a few hydrogens around that aren't deuterium, right? Because the whole solvent is deuterized, all of it. So at that point, you're just pushing equilibrium this way, because there's so much of this around, and you can deuterate the alpha hydrogens. You cannot deuterate hydrogens are you going to deuterate if you try to do it with this? If you have as much, as possible, as much D2O as you want. How many acidic hydrogens are there? These guys, right? 3. This one, is this acidic? It's not even on your pKa table. And I tried to look up the pKa, and it is stubborn. I'm pretty sure I have it somewhere, like, in my handwritten notes, that are somewhere from my master's level class. Like, he just liked to give us the pKa's of stupid things like this, where it's like, you'll never need to know the pKa. The pKa of this is no. But it's not acidic. Like, it's like carbon hydrogen level stuff. It's like, no thank you, you can't make me. So we're gonna get, eventually, we can get D3C. That. So this kind of labeling can be done, is often done for excuse me. Well, you can do this specifically to find out experimentally which hydrogens are acidic, because, well, if you put enough deuterium in there and wait long enough, most of the things that are going to be able to be switched out are going to be switched out. So if you then run an NMR and you see a whole lot of one peak that's like, clearly none of this was replaced, then you know that that guy is not particularly acidic. But also, you can do this to for isotopic labeling. There we go. To isotopically label. There we go. Parts of speech. It's, chemistry, like, isotopic label is like, that's a noun, isotopic labeling, okay? And then, in order to isotopic label, and I just want to conjugate the end of it, and I don't know how, isotopically label, but we don't talk like that, sorry. So, we can do that. That's how we can deuterate things. Methanol D1, methanol D, ethanol D, or methanol D1, ethanol D1, they're just deuterated right there at the OH group. That is way cheaper to buy than like fully deuterated methanol or ethanol. If you're doing like, NMR and stuff. I mean, I don't think this is the most useful NMR solvent, but it exists. Okay, the other thing we can do at alpha carbons for now is alpha halogenation. So, this is going to be really similar to when we we'll just do it. This is this can be catalyzed by acid or base, and I don't think I've got anything. Yeah, I don't have anything on the next 2 slides. They just say mechanisms and more mechanisms. So let's do this guy, and yeah, cool. Come back, mouse. Yes, we're gonna finish chapter 16 before before the break. Okay, it's 9:32, right, 8:32. That clock was right yesterday. The hour was correct. Okay, let's do acid on this side. Acid. Now I won't pretend I'm tall. I'm trying to reach the top of the board. And we're gonna do, for color coding purposes and so that when I lose words, I have a visual reminder of which one has more electrons. Alpha catalyzed, acid catalyzed alpha hydrogenation, halogenation. God, words are so hard. Okay. Halogenation. We're putting a halogen alpha to a carbonyl, and we're using acid to do it. There. Let's not use the words that just sound like other words. Really easy for me to say the wrong thing. All right. Okay, we're going to I don't know if I'm really going to color code these words. But we're going to draw out the carbons like this, because both of these carbons get to play the game. So we have this, R, H. Okay, this guy. And the first thing that we do is tautomerization. Stay there. All right. Tautomerization is going to have something. Oh wait, this is acid, right? Yeah, this is acid catalyzed. So in acid catalyzed, first we're going to end up doing that, right? So that then when we have, there, A minus is the same thing as B, but reminds us we're in acid instead of base. So there's a little bit of this conjugate acid, or conjugate base from the acid. When that guy steals this, this folds down and this goes up, and we get and we don't get a negative charge on our oxygen because, well, this is very, very super acidic, right? So if you have any base around, that's not even going to happen. So we did that instead because we're massive. Is this okay? Because I kind of condensed this, but okay, we have that. Cool. Second, we get a new bond, new bond between our pi bond and the electrophiles. So we end up, okay, that's how I'm going to draw this. We've got that's our nucleophile now. That, and we've got okay, we've got this. We've got, technically this is our nucleophile. This is our electrophile. So we do an attack that way, right? And we end up with bromide getting kicked off, and we have, well, okay, wait. Visually, this isn't wrong, but visually, I want this arrow to go that way to indicate that it's going to hang out on that carbon. Like the electrons come from in between, but technically that mechanism arrow doesn't actually specify which carbon that goes on, which is not overly useful if I make it look visually like it's the wrong one. Red. There. And you've seen something like this before back in your chapter last month-ish on carbon-carbon double bonds, alkenes. So this is, right, electrophilic substitution, right? Yeah, electrophilic addition. Yeah, electrophilic addition. So, technically that would give us, okay, yeah. the same step, because I could draw the product and have positive charge on here, but like, why do that if I can make all the octets full, right? So we're gonna do that. So that attacks that, that comes down and reforms that, and we get let's see. Okay, then we get this. Cool. Oh, wait, we're not here yet. We're here, because we're an acid, right? So we've got this guy, which is awesome. It looks like we're almost done, but like, well, technically we haven't entirely formed our carbonyl again, because we've got this mess going on, so why are they putting... Oh, okay. This is claiming in your slides when you see this, it's going to be really oddly specific about what deprotonates this, because really it's just, well, let's add that in blue for the A minus goes bloop. Then we have that, and this goes, hey, cool, you can have that. And then we get alpha substituted halogen.
So now HBr is formed?
Well, so I don't want to write HBr just because, is HBr a strong acid? Yeah. Yeah, so partly I just don't want to write it because HBr is a strong acid, so I just don't, like, if H and Br are just ions that hang out, like, as soon as they hit anything where they can just get as far away as possible, they're just like, whatever, see ya, whatever, then I don't want to show that stealing it, because that's really not going to happen at all. And your slides are showing us, they're very specific, and they want us to have acetic acid as our acid, which means that we've got this as our acid, and they want this to go ahead and steal the hydrogen up there. Bloop. So, I don't know. I mean, one could just as easily call it A minus, or we could call it HA, because that's a little closer to this, and then we would end up, instead of with HA at the end, is what we formed there, we would end up with H2A, which is equivalent to that we end up with after we use that. Yeah? I don't know why they're so specific as to draw this, but like, that's plenty. Who cares about what else is like happening near it, right? Base promoted. Okay. Base promoted, we're gonna do basically the same thing, except now we've got that. And we've got a base, and I get to call it, in case you're wondering, they label these as slow, not because, because this is the whole tautomerization, not because this is just an acid-base thing. This is a fast step, and this is a fast step, in case you were wondering. Okay, then we have, sure, we'll call it OH minus, that's fine. OH minus, and it's gonna go, hey, that's a really nice hydrogen there. It would be a shame if something happened to it. And we're gonna do all of that because why have a charge or a lone pair on a carbon when we could stick the lone pair in an oxygen and everybody's happier? So, there. Now we've got this. And now it kind of looks like a thing that is, I mean, yeah, and yes, this is a, oh, okay, yeah. Your book doesn't like to do this in one step. I do. I think that's dumb to just put a lone pair in here and then show you the resonance stabilized cation or anion, but like, it's resonance stabilized. We just put it in the right way. This guy is kind of slow. And then we take, yeah, that's the only thing. We take carbon minus R. And we do exactly what we just did with electrophilic addition. But in this case, we're doing a substitution, right? So this looks almost exact, like is very reminiscent of electrophilic addition, which is what we've done before. But it's not addition because we got rid of that hydrogen and we're replacing it with the bromine, right? So basically, we're not in the end breaking a double bond. We're just moving the double bond, we're moving the double bond somewhere else where it's gonna be able to go through a mechanism like this. And then we can just reform that double bond over here so it's not technically substitution, or so it's not technically addition. And that's all there is, because this was in base. So, I'm gonna give you a little bit of time to write this down before I technically start our break, because like, I don't know, this is a long class. And we did it! This is the end. After this, I have, okay, fine, I have one slide with words on it. That's all, so we did it. We did it, and we get to start chapter 17.